Hello everyone. This video's topic is on the concept of derangements. And what is a derangement? It's a permutation where nothing stays put. So for example, if I have the numbers 1, 2, and 3, we know that in general there's three of them, so there's n factorial permutations. So there's 6 permutations of this. We can write them out. 1, 3, 2, 2, 1, 3, 2, 3, 1. 3, 1, 2, and 3, 2, 1. So with the original, that's 6 permutations. But if we ask which of these, for which of these do none of the numbers stay in their original position, then we really only have a couple. We have this one, 2, 1, 3, and this one, 3, 1, 2. Those are called derangements of the original permutation. And so for 3 objects, there's only 2 derangements. And so then we can try to generalize this. We can say, can we find a formula for this? Is there a way we have of determining how many derangements there should be if we have more objects? So let's just do a little bit more of an example, just to fill out the series a little bit. So actually, let's start even simpler, just to get the first few terms in the series. So like, for example, if I have just one object, then I only have one permutation, and that doesn't move anything. So there's 0 derangements there. So we would say d1 equals 0, where d sub n is the number of derangements. If I have 2 objects, there's only 2 permutations, and one of them just swaps them, and that is a derangement. And so there's a d2 equals 1. We just saw the example that if I have 3 objects, there's 2 possible derangements. There's 3, 1, 2 and 2, 3, 1. So we say there's 2 derangements there. And now let's just work through a little bit of an example and start to maybe think about how we can maybe generalize this. Let's look at D4, all the permutations of 4 objects. And let's see if I could do it, if we can think about it in a nice way without writing out all the permutations. Because we know that for 4 objects, there's 24 permutations, which isn't too many, but it'd be nice if we didn't have to write them all out. So first example, we know, we know the 1 can't stay put, so we can't have a 1 in the first position. So we could try a 2 in the first position. And so we could try, let's swap the first 2. But then we have 2 left, and we can't just do 3, 4 because those would stay put, so we need to swap those as well. So certainly that's that's a derangement of the 4 objects, but it's not going to be the only one. But it's the only one where we just swap the first 2. If we swap the first 2, then we're forced to swap the remaining 2 because that's all we can do. Then we can say, okay, what else can we do? We could swap 1 and 3 maybe. So we could say 3, 1, and then again we have sort of the same choice. We can't leave the 2 and the 4 where they were and have it still be in derangement, so this has to be a 4, this has to be a 2, so that's another derangement. And we could keep going with this idea, swap the 1 and the 4 for 1, and again we can't leave the 2 and the 3, can't leave them stay put, so there's another derangement. But have we got them all? Are there more than 3? There should be. Excuse me. Because we can think of some others. So let's look at what happens if we swap. So that's sort of swapping pairs at a time, but is there a way we can do more than that? Because we could start looking at the 2 and swap that with the 3, but we already actually did that. We did swap the 2 and the 3, and then we're forced to swap the 1 and the 4, so we counted that one already. But another way to think of this is if we take all the numbers and like just shift them over one position, that's going to be a derangement. It's called a cyclic permutation. But if we shift everything by 1, then everything has moved, and we're going to get a derangement. So in fact, one of these is already that, this middle one, 3, 4, 1, 2, that's actually, if I shift everything by 2, that's a cyclic permutation of the original, but I've got some more. I could do 2, 2, 3, 4, 1. I haven't done that one yet, so that's a derangement. I already have 3, 4, 1, 2, but I could also have 4, 1, 2, 3. 4, 1, 2, 3. That's a cyclic permutation. Not done yet. There's more. Because we know, actually, if we look at some of these others that we already did, especially here, we have 4, 3, 2, 1. That's actually just reversing the original list. And so I could also reverse the list. In this case, that's a derangement because it's an even number of objects. If it was an odd number, that wouldn't have worked because the middle one would have stayed put. But here, we have an even number of objects. I can reverse the list and get a derangement. But I can also do cyclic permutations on that because you notice, in fact, 2, 1, 4, 3, this top one, is actually just the 4, 3, 2, 1, but shifted over by 2. So we could also get a couple more along those lines. We could have 3, 2, 1, 4. We don't have that already. And then let's see, do we have another one? We've got the 2, 1, 4, 3. We don't, 1, 4, 3, 2 doesn't count because then the 1 stays put. And then 4, 3, 2, 1 we already have, 3, 2, 1, 4, yeah. So I think we've got them there. So we've got 6 so far, but I happen to know that there are more. So what are we missing? Well, what's another way of thinking about these? We looked at sort of swapping 2 objects and looking at that. But let's see if we can find a couple more. Because so far I've got 2 that begin with each number. I've got 2 that begin with 2, 2 that begin with 3, and 2 that begin with 4. Is there another one that begins with 2? So I can have the remaining things. I can have 1, 4, 3, 3, 4, 1. But is there another permutation there that will count as a derangement? Well, I could put the 4 here. 2, 4. I can't put the 3 next, so that has to be the 1, but then I could put the 3 there. So that's actually another derangement that I haven't done yet. And you notice that's not any kind of cyclic permutation. And it's not just a simple swapping of pairs, but it's something that's a little bit more involved, but it's a derangement. And I'm going to be able to do something similar with beginning with 3 and beginning with 4. So if I begin with 3, let's see, what do I have already? I have 3, 4, 1, 2, and 3, 2, 1, 4. So I can have 3, 1, and then I can't have 2, 4, because then the 4 doesn't move, but I can have 4, 2. So that's a derangement. And then finally, I didn't leave myself much room here, but I'll squeeze it in at the bottom. I've got 4, and then I can put a 2 next. 4, no, I can't put a 2 next. Never mind. But what can I put next? I can have a 1 or a 3. So if I put a 3, though, I already have 4, 3, 2, 1, but I could also have 4, 3, 1, 2. I haven't done that one. Because there, again, none of the others stay put. So that's it. 1, 2, 3, 4, 5, 6, 7, 8, 9. I happen to know that that's all of them. But maybe you can convince yourself that's all of them. But at this point, what we'd like to do is try to see if we can find a more general formula. So far, we've got a little bit of a pattern, 1, 2, 9, or really 0, 1, 2, 9. And the question is, can we find a pattern where we can actually write this out as a simple formula? And can we use some thinking about how to form derangements to do that? Also, as an aside, we could have started with the number of derangements of 0 objects as the starting to our series. And you might wonder how that makes sense, but there's actually a way to sort of think of that in making sense. If you have no things, then how many ways can you rewrite no things in which no thing stays in the same place? And so, but I'll leave that as an exercise for you to think about what that might be. It's not too important for our purposes of defining a more general formula, but it's an interesting question. But we want to see if we can find a way of writing the number of derangements of n objects, and especially it would be nice if we could find a way of writing it in terms of some previous value in the series. And so let's think in general about the possibilities and see if we can't come up with something. So in general, I'm just going to number the objects 1, 2, 3, 4, 5, and we'll just imagine keep going. And we're looking for derangements of that. So nothing can stay in the same place. So for example, I can't pick 1 for the first number, but I could pick any of the other numbers. So I've got n minus 1 choices there. If I go up to n here. But let me just, for the purposes of an example, let me write this in a different color. Let's pick 2, just to keep this example here. I could pick 2 to be the first number in the derangement, or I've got any of n minus 1 choices that I also could have picked from. But now, what does my decision process look like? Well, there's basically 2 cases that I can think about. One is, and let me actually draw this with some arrows. So I've made this choice. I'm just going to, as example, say 2, but really I've got n minus 1 possibilities there. So that's something to keep in mind. But now I've got 2 possibilities. This is meant to be an arrow, not a greater than or less than. I could say, well, let me just pick, I skipped over 1, so let me pick 1 as my second number, because then the 1 won't be in the same place too. So I basically just swap the first 2. Or whatever I picked for the first number, I just swap 1 with that. Then, what do I do for the rest of the list? Well, for the rest of the list, I've got 3, 4, 5 up to, 3 up to n. And I just need to pick a derangement of n minus 2 objects. And so, but how many of those are there? There's just whatever the number of derangements is for n minus 2 objects. So once I've picked the 2 and the 1, I have dn minus 2 possibilities left, because there I'm just trying to make a derangement of the remaining elements of the list. On the other hand, what if I don't, what if I picked something else? I didn't pick the first element here. So what if instead of 1, I picked, again, I'm going to pick a specific example, but I've got n minus 1, or n minus 2 things that I could have chosen from. And I pick something else. But what do I need to do? I'm basically looking at the list. I've already picked 2. And one way to think about this is I'm going to try to write this out. I've got a list 1, 3, 4, 5, on up to n. And I'm not going to pick the 1. But I'm going to pick something else, and then I need the rest of that to be a derangement. So I need to pick, something else here, but then everything else also has to be a derangement. Since I'm not picking a 1, this whole thing is going to be a derangement. So it really just amounts to the problem of if I pick 2 and then pick something else, then I'm just basically taking a derangement of n minus 1 objects. Because I'm putting something else where the 1 was, and then the rest of it also needs to be a derangement, so it's basically a number of derangements of n minus 1. And so that's the argument that I can put together to find a recurrence relation. what we can call a recurrence relation, where we can write the number of derangements of length n is equal to, remember here I just used 2 as an example, but I could have chosen anything and the rest of the argument still follows. So in the case where I picked 2, I had n minus 1 possible choices. And then one of two things could happen. Either I have one possible choice and then dn minus 2 derangements, or I pick something else such that I'm basically just making an n minus 1 derangement. And so that's my general formula for the number of derangements up to n. And so let's see if this works. Because we've already got some examples, so let's see if we can. We need to know at least a starting 2. So we could actually say, well, okay, does this work for d3? It says d3 should be 2 times d2 plus d1, which d2 was 1 and d1 was 0, so that should just be 2. So yeah, d3 is 2, that works. Does it work for d4 as well? It says d4 should be 3 times d3 plus d2. That's the same as 3 times 2 plus 1, which gives me 9, which is what we found by inspection and counting. So it seems to work so far. And in fact, that is the general formula for the number of derangements. But now we've written it in this important form, what we call a recurrence relation, where each element in the sequence can be defined in terms of previous elements. And so what we're going to move on to very soon is one of our next topics, is just ways of rewriting recurrence relations and solving them in terms of other things. Because the question that we have here is, maybe can we even solve this and write an even simpler version of it? Can we write dn in terms of just n? Or could we at least maybe take out the n minus 2, write it in a different way? Those are all questions that we could ask. And so that's one way, that's one avenue we could take as to where we go next. By the way, let's just fill in a couple more elements in this series, just out of curiosity. This lets us say d5 will be 4 times the previous 2 added together, so that's 4 times 11, so that's 44. And we could even go d6. I'll squeeze it in over here. That's going to be 5 times the previous 2 added together. 44 plus 9 is 53, and so 5 times 53 is, let's see, 265, right? And so on. So that's a sequence we could define as the number of derangements. Another interesting avenue that we could take with this is, that I will leave as sort of an open question, but it's an interesting one. We could talk about, we define derangements as a permutation that leaves none of the original elements in place. If I go back to my example with 3, we had, this is a derangement, and sorry, no, that's not a derangement. What are my 2 derangements? My 2 derangements are 3, 1, 2 and 2, 3, 1. You could also ask the question, so each of these is a derangement relative to the original permutation. But another interesting question you might ask is, are they derangements relative to each other? And in fact, you can see here that yes, in this case, these two are also mutually derangements. 312 and 231 have no elements in the same place. But is that so? In this case, we have sort of a set maybe of things that are all sort of mutually deranged. I don't know if there's a better term for that, but that's my term and I'm going to stick with it. But if we go to 4 objects, does this still hold true? Are all derangements going to also be mutual derangements? And I think we can see that they will not. So let me just, for example, well, we can already see that because remember we had several derangements that all started with 2. So of course those aren't mutually derangements. We had 2, 1, 4, 3. That's a derangement of the original. But we also have 2, 3, 4, 1. That's a derangement of the original. So this pairing is a derangement. This pairing is sort of mutually deranged. But these two are not. The 2, 1, 4, 3 and the 2, 3, 4, 1. So you could say, okay, is there some set? Is there some group? I haven't really talked about sets in detail, but whatever. Is there some bunch of permutations that are sort of all mutually deranged, as I might call it? And so there are going to be a few. I'll claim that there's one easy set we could find, which is, again, we sort of talked about it a little bit. We said one way to form derangements is we can do a cyclic shift. So for example, this 2, 3, 4, 1, that's a cyclic shift. We could also do 3, 4, 1, 2, that's cyclic. And finally, we have 4, 1, 2, 3. Those are all cyclic shifts of the original. They are also derangements of the original. But because they're cyclic shifts, they're also cyclic shifts relative to each other. So they're all derangements relative to each other. So like 2, 3, 4, 1 and 3, 4, 1, 2, no 2 elements in common. Those are sort of mutually deranged. 3, 4, 1, 2, 4, 1, 2, 3, mutually deranged. 4, 1, 2, 3 is mutually a derangement of 2, 3, 4, 1. I'm running out of space to put arrows, but basically all those combinations, nothing remains in the same place. Because if I do a cyclic shift, I'm moving everything over by 1, so of course nothing stays put. So one thing we can already see is that, yeah, these cyclic permutations are in some sense going to be special. Or at least there's something interesting going on there, and in the sense that they're permutations where nothing stays put relative to the original, and they're all sort of mutually have that property. And so we'll come back to that maybe at some point, like when we talk about groups, maybe, because we'll be. It turns out these cyclic permutations are sort of interesting in their own right. But for now, I will leave things at that, and we'll move on to another topic in our next video.